Have you ever looked up at the night sky and wondered if this is all there is? The stars scattered across the darkness, the galaxies spinning in the void, our own small planet orbiting an ordinary star. It seems vast enough already, infinite even. But what if everything we can see, everything we have ever observed with our most powerful telescopes, is just a tiny fraction of what actually exists? What if our universe, with its 100 billion galaxies and countless worlds, is not alone? For most of human history, we believed our world was the center of everything. Then we discovered we orbit the Sunday. Then we learned our sun is just one star among billions in a galaxy. Then we found that our galaxy is one among billions of galaxies. Each discovery pushed the boundaries of reality further outward, revealing a cosmos far larger and stranger than we had imagined. Now, at the edge of our understanding, scientists are asking an even more profound question. They are wondering how many multiverses are there and whether the universe we call home might be just one bubble in an infinite sea of other universes, each with its own laws, its own stars, its own stories, unfolding in ways we can barely comprehend. Some of these universes might be almost identical to ours. Others might be so different that the very concept of matter and energy would be unrecognizable. Some might be infinite in extent. Others might branch into existence with every quantum event, creating endless parallel realities where every possibility plays out. The idea seems like science fiction, but it emerges naturally from our best theories about how the cosmos works. From the equations of quantum mechanics to the mathematics of cosmic inflation, multiple lines of evidence point toward the same strange conclusion. We may not be living in a universe at all. We may be living in a multiverse. Tonight, we are going to explore these ideas together. We will journey beyond the edge of what we can see, peering into the fog of unknowing that still surrounds us. And perhaps, as you drift toward sleep, you will find yourself floating through infinite possibilities, wondering which version of reality you will wake up in tomorrow. In the year 1828, an amateur cartographer named Edward Quinn completed his life's greatest work. It was called the Historical Atlas, a remarkable collection of maps unlike any that had come before. The atlas was published 2 years after Quinn's death, and it depicted something quite extraordinary. It showed our knowledge of the world as a flickering light, a gentle glow that slowly pushed back vast clouds of ignorance. These clouds, drawn in dramatic swirls across the pages, represented all that we did not yet know. As you turned through the atlas, the clouds gradually lifted, unveiling continents and ancient civilizations that had been shrouded beneath them. Quinn was not a professional geographer. He had no formal training in cartography, yet his passion for understanding how human knowledge grows led him to create something truly unique. Each map in his atlas was not merely a representation of land and sea. Each map was a philosophical statement about the nature of discovery itself. The clouds he drew were not arbitrary decorations. They were carefully positioned to show what each civilization knew, and more importantly, what they did not yet know. It was a visual representation of ignorance, retreating before the advance of exploration and learning. The Atlas begins its journey in the year 2348 before the Common Era. Quinn started with the biblical narrative, the dispersal of Noah's descendants across the earth. The maps show only tiny patches of known land. The clearing of these illustrated clouds mirrors the expansion of European exploration into the lands that lay beyond their familiar shores. In those earliest pages, the known world consists of little more than the fertile lands between the Euphrates and Tigris rivers. Everything else remains hidden beneath artistic representations of mystery and the unknown. These ancient civilizations, thriving in Mesopotamia, had their own sophisticated understanding of geography. They created clay tablets with maps etched into them, showing cities and trade routes. But their world was small, bounded by mountains and deserts and seas. Beyond those boundaries lay the realm of myth and speculation. Dragons and monsters populated the edges of their mental maps, symbols of the dangerous unknown. As time marches steadily forward, you can step through the pages of the Atlas, like walking through history itself. You pass through the exodus of the Israelites from Egypt. You witness the rise and spread of the Roman Empire. With each turning page, more and more of the world becomes visible. The clouds retreat, new coastlines emerge from the fog of uncertainty. By the time you reach the early 19th century, something remarkable has happened. The clouds have been fully dispersed. All the continents are now visible on the maps. There appears to be no more land left to discover. The age of exploration had fundamentally transformed human understanding. Portuguese navigators had sailed down the coast of Africa. Christopher Columbus had crossed the Atlantic. Ferdinand Magellan's expedition had circumnavigated the entire globe, proving once and for all that the Earth was round. Captain James Cook had mapped the Pacific with unprecedented accuracy. The blank spaces on maps had been filled in. The monsters and dragons had been replaced with accurate coastlines and proper latitudes and longitudes. Of course, this atlas tells only one story. For an artist working in China, or India, or Australia, or in the Americas, the focus would be entirely different. Each culture had its own origin story. Each civilization began with its own small portion of the world, surrounded by its own unique darkness. Each people group slowly pushed back their own clouds of unknowing. And indeed, these clouds that Quinn drew on his maps were not solely geographical in nature. They represented something deeper and more universal. The Chinese, for instance, had their own rich cartographic tradition stretching back thousands of years. Their maps placed China at the center, the Middle Kingdom, surrounded by tributary states and barbarian lands beyond. Islamic scholars in the medieval period created remarkably accurate maps, preserving and extending the geographical knowledge of the ancient Greeks. The Polynesian peoples navigated vast stretches of the Pacific Ocean using sophisticated mental maps encoded in songs and stories, reading the stars and the patterns of ocean swells. Each tradition represented a different way of pushing back the darkness of the unknown. All human endeavors begin in a fog of mystery. This is true whether we are exploring physical geography or the nature of reality itself. This fog only begins to clear when we learn something genuinely new. Just as the mapped surface of the Earth was once hidden beneath imaginary clouds, the universe itself has been shrouded in layers of cosmic mystery. Over the last few hundred years, we have turned our collective attention toward the heavens above. With our most powerful telescopes, instruments of remarkable precision and sensitivity, we have peered deeper and deeper into the vast cosmos. The transition from mapping Earth to mapping the cosmos represents one of the great intellectual shifts in human history. When Galileo first turned his telescope toward the heavens in 1609, he saw things no human had ever seen before. The moon had mountains and craters. Jupiter had its own moons orbiting around it. Venus showed phases like our moon, proving it orbited the Sunday. These observations shattered the ancient Aristotelian view of a perfect, unchanging celestial realm. We have spied countless stars scattered across the night sky. We have discovered enormous galaxies, each containing hundreds of billions of stars. We have found black holes, those mysterious regions where gravity becomes so intense that not even light can escape. We have spotted planets orbiting distant stars, worlds that might harbour conditions suitable for life. We have even managed to peer backward through time itself, looking over 13 billion years into the past. There, in the most distant reaches of space and time, we have seen the very afterglow of creation itself, the faint echo of the Big Bang that gave birth to everything we know. Each of these discoveries required new technologies and new ways of thinking. Black holes were first predicted mathematically by Carl Schwarzschild in 1916, based on Einstein's equations of general relativity. But they seemed so bizarre that even Einstein doubted they could really exist. It took decades of observational work before astronomers accepted that these objects were real. The first confirmed black hole, Cygnus X-1, was identified in 1971 through its X-ray emissions as it consumed matter from a companion star. The discovery of planets around other stars, called exoplanets, required extraordinary precision. The first confirmed exoplanet orbiting a Sun-like star was found in 1995 by Michel Mayor and Didier Queloz. They detected the planet not by seeing it directly, but by measuring the tiny wobble it induced in its parent star. Since then, thousands of exoplanets have been discovered, revealing that planets are common throughout the galaxy. Some orbit in the habitable zone, where liquid water could exist on their surfaces. The question of whether life exists on any of these distant worlds remains one of the great unanswered questions of our time. And we have done more than simply look into the past. We can now deduce the future history of our universe with reasonable confidence. We can look forward to the days when the last star will flicker and die, an event that will occur trillions upon trillions of years from now. We can even imagine further still to the unimaginably distant future when matter itself begins to decay, when black holes slowly evaporate one by one through a process called Hawking radiation. The universe has steadily given up its secrets to us. The cosmic clouds have been lifted, seemingly one after another. The far future of the cosmos is in some ways easier to predict than its past. We understand the laws of physics well enough to extrapolate forward. In about 5 billion years, our sun will exhaust its hydrogen fuel and begin to swell into a red giant, eventually engulfing the inner planets, including Earth. Other stars will follow similar paths. The smallest stars, red dwarfs, will burn for trillions of years before finally fading. Eventually, all the stars will go out. The universe will enter what is called the degenerate era, where dead, stellar remnants like white dwarfs and neutron stars dominate. Even these will eventually fade to darkness. It might now appear to the casual observer that we have learned all there is to learn about the cosmos. The map seems complete. The fog seems cleared. But history teaches us to be cautious about such conclusions. There is a famous example that serves as a warning. Simon Newcomb was a remarkable polymath, a man of learning who made contributions to many fields. In 1888, he boldly claimed that humanity had essentially reached the limits of astronomical knowledge. He suggested that all the major discoveries had already been made. Then Newcomb died in 1909, and he passed away just as Albert Einstein was beginning to upend the entire world of physics with his revolutionary theories. It is always, without exception, a bad idea to bet against further discoveries. Newcomb's mistake was understandable in its historical context. By the late 19th century, physics seemed nearly complete. Newton's laws of motion and gravity explained the movements of planets with extraordinary precision. Maxwell's equations unified electricity and magnetism into a single electromagnetic theory. Thermodynamics explained heat and energy. There were a few small puzzles remaining, but most physicists thought these would be quickly resolved. Then came quantum mechanics and relativity, completely transforming our understanding of reality at both the smallest and largest scales. The 20th century brought more revolutionary discoveries than Newcomb could possibly have imagined, And so this is precisely where scientists find themselves today, standing at a curious threshold. They stand tall upon towers built from complex mathematical equations, elaborate theoretical frameworks, and remarkable observational tools. From these towers, they try to peer even further into the fog that still surrounds us. But unlike the geographical clouds in Quinn's historical atlas, this is not simply a fog created by distance alone. These are clouds of a different kind altogether. These are clouds that linger all around us, in every direction we might look. They exist within us, woven into the very fabric of our existence. They stretch out before us into the future. These clouds represent entirely new universes, realities that are born beyond our cosmic horizon. Some of these universes might have existed in our distant cosmic past. Others might even exist somehow inside our own universe, nested within it. With every passing instance, with every quantum event that occurs, new possibilities might branch into existence. As our knowledge of theoretical physics has grown more sophisticated, ideas that once seemed completely radical have gradually forced their way from the realm of fantasy into the realm of genuine possibility. Some physicists now argue that these ideas have moved beyond possibility into actual probability. Theories about multiple universes, collectively known as multiverse theories, have proliferated throughout the scientific community. These theories are attempting to answer some of the deepest questions we can ask about existence itself. They seek to explain what we are, what the entire cosmos is, and why anything exists at all. The landscape of multiverse theories is remarkably diverse. Some propose parallel worlds where infinite versions of you are living out every possible variation of your life. Others suggest vast, barren deserts of endless nothingness stretching between bubble universes. Scientists are actively working to blow away this cosmic fog of unknowing, hoping to reveal the true structure of reality. What they are discovering is a warped sort of Russian doll, layers of infinities nested both within each other and existing right next to one another. Welcome to the multiverses. According to careful calculations made by the European Space Agency, there are approximately 106 sextillion stars in the observable universe. That is a number so large it becomes difficult to comprehend. These stars are not scattered randomly across space. They form enormous structures, huge filaments and clusters that stretch across hundreds of millions of light years. But on a more personal level, on a human scale, have you ever wondered what the night sky looked like on the day you were born? What patterns did the stars make on that specific date and time? To put the number of stars in perspective, imagine you tried to count them. If you could count one star every single second without stopping, it would take you over 3 billion years to count all the stars in the observable universe. That is nearly as long as life has existed on Earth. And that is just the stars we can see. Beyond our cosmic horizon, there may be infinitely more. The story of how we came to understand the true scale of the universe is a fascinating one. It begins with a famous debate that took place in April of 1920. A great debate was held at the Smithsonian Museum of Natural History in Washington, or District of Columbia. This was not a casual discussion. It was a formal event, attended by many prominent figures in the scientific community. On the stage stood two men, both renowned astronomers of their time. The debate took place in an era of tremendous change in astronomy. Telescopes were getting larger and more powerful. Photography had recently been applied to astronomical observation, allowing astronomers to capture faint objects that could not be seen by eye alone. Spectroscopy was revealing the chemical composition of stars. The tools of astronomy were advancing rapidly, but fundamental questions about the cosmos remained deeply controversial. The first was Harlow Shapley, Shapley had become well known for his meticulous work mapping the locations of stars throughout our Milky Way galaxy. He had made significant contributions to our understanding of the galaxy's structure and size. The second man was Heber Curtis. Curtis held his own impressive credentials. He was the first person to observe a thin, peculiar stream of material emanating from an object catalogued as Messier 87. Though Curtis did not know it at the time, he had discovered something extraordinary. He had observed a relativistic jet, a stream of matter being ejected at nearly the speed of light from an immense black hole lurking at the heart of that distant galaxy. The topic of their debate was deceptively simple, yet profoundly important. The question they were addressing was this: just how big is the universe? It seems like such a straightforward question, but the answer would reshape our entire understanding of reality. The two camps presented their arguments to the assembled audience. Shapley stood firmly in his position. He argued that the cosmos was actually quite small, at least by cosmic standards. The stars of the Milky Way, he claimed with confidence, constituted the entire universe. That was all there was. There existed nothing beyond the boundary of our galaxy. Shapley acknowledged that astronomers had observed several strange nebulae through their telescopes, fuzzy patches of light scattered across the night sky. But these nebulae, he insisted to the audience, were simply features buried within the vast expanse of stars that made up the Milky Way. They were local phenomena, nothing more. Shapley's argument was based on several lines of evidence. He had measured the distances to globular clusters, dense, spherical collections of stars that orbit the Milky Way. His measurements suggested the Milky Way was much larger than previously thought, perhaps 100,000 light-years across. If the galaxy was that enormous, Shapley reasoned, then those fuzzy spiral nebulae could easily fit within it. There was no need to invoke the existence of other galaxies. Curtis, however, strongly objected to this interpretation. He was no fan of Shapley's compact cosmos. Instead, Curtis argued that the universe was much, much larger than most astronomers of the time were comfortable accepting. The spiral nebulae that had been observed, those mysterious fuzzy patches, were not contained within the Milky Way at all, Curtis declared. Instead, each one existed many millions of light-years away from our own galaxy. Each spiral nebula was what he called an island universe. Each was an individual galaxy in its own right, a vast collection containing billions upon billions of stars. And if this were true, Curtis reasoned, there could be uncountable numbers of such galaxies existing far beyond the edge of the Milky Way, stretching out into space as far as anyone could imagine. Curtis had his own evidence to support this view. He had studied the novae, exploding stars, found in these spiral nebulae. They appeared much fainter than novae in our own galaxy, suggesting they were much farther away. He had also noted that the spectrum of light from these nebulae looked like the combined light of many stars, not like the glowing gas that made up the nebulae within the Milky Way. These observations pointed toward the nebulae being distant collections of stars, separate galaxies in their own right. Eventually, after both men had presented their evidence and arguments, the debate came to a close. The audience had been taken on quite a wild intellectual ride across competing visions of the universe. But when the evening ended, there was no clear winner. Neither Shapley nor Curtis had definitively proven their case. The two astronomers went their separate ways, and the fundamental question about the size of the universe remained frustratingly unsolved. The great debate became legendary in the history of astronomy, not because it resolved the question, but because it so perfectly captured a moment of profound uncertainty. Both sides had compelling arguments. Both sides had evidence. Yet the truth remained elusive. It would take new observations and new methods to finally settle the matter. But even as the debate concluded in a draw, things were already changing rapidly. On the other side of the North American continent, far from Washington, a young astronomer named Edwin Hubble had recently joined the staff of the Mount Wilson Observatory in California. Hubble was on a personal quest. He wanted to answer the question about the size of the universe once and for all, to settle the matter with solid observational evidence rather than theoretical arguments. Hubble was a complex and driven individual. He had studied law at Oxford University as a Rhodes Scholar before returning to America and deciding to pursue astronomy instead. His colleagues sometimes found him arrogant and self-promoting, but no one could deny his observational skill and his dedication to solving the great questions of astronomy. He understood that the debate between Shapley and Curtis could only be resolved through careful measurements, not through arguments. The timing of Hubble's work was remarkably fortunate. The world's largest telescope had just been installed at Mount Wilson. This was the 100-inch Hooker telescope, an instrument of unprecedented light-gathering power. It was the ideal tool for surveying the night sky and charting the true distances to heavenly bodies. Hubble recognized the opportunity before him, and he knew exactly where to begin his observations. The Hooker telescope was a marvel of engineering. Its primary mirror, 100 inches in diameter, had been cast from a special low-expansion glass. The mirror alone weighed several tons. The entire telescope structure towered above the mountaintop, housed in a massive rotating dome. On clear nights, astronomers could open the dome and swing the telescope to point at any object in the sky. The light-gathering power of this instrument far exceeded anything that had come before. His first target was the Fuzzy Nebula, located in the constellation of Andromeda. This nebula had puzzled astronomers for years. Hubble knew that previous observers had managed to see individual stars within the Andromeda Nebula, tiny points of light barely visible even through powerful telescopes. But the critical question remained unanswered. Just how far away were these stars? They could potentially be intrinsically faint stars located relatively close to us, within the bounds of the Milky Way. Or they could be extremely luminous, brilliant stars observed at a very great distance, far beyond our galaxy. Astronomical evidence had actually been building for several years before Hubble turned his attention to the problem. In fact, as far back as 1917, it had been Heber Curtis himself who discovered an exploding star within the Andromeda Nebula. This was a nova, a stellar explosion that briefly outshines all the other stars around it. Curtis went searching through older photographic plates taken of the region, and he managed to spot 11 more novae. These were much fainter than any others that had been observed previously, which suggested something interesting about the distance to Andromeda. The faintness of these novae was a crucial clue. If Andromeda was simply a nearby nebula within the Milky Way, the novae should have appeared brighter. Their faintness suggested that Andromeda might be very far away indeed, but this evidence was not conclusive enough to settle the debate. Curtis needed something more definitive, a more reliable way to measure cosmic distances. But Hubble was searching for something different, something that would provide more definitive proof. He was carefully scouring the Andromeda Nebula for stars whose brightness varied over time. Many types of stars can change their brightness for various reasons, but Hubble was hunting for one particular kind of variable star, a class known as Cepheid variables. These remarkable stars are cosmic lighthouses of sorts. Cepheid variable stars possess a unique property. Their brightness varies with a regular, predictable beating pattern, brightening and dimming in a steady rhythm. In 1912, an astronomer named Henrietta Swan Leavitt made a crucial realization while studying these stars. she discovered that the length of time a Cepheid takes to complete one full cycle of brightening and dimming depends directly on how luminous that star truly is. Fainter Cepheid stars beat rapidly, cycling through their brightness changes in just a few days. Brighter, more luminous Cepheid stars beat much more slowly, taking weeks or even months to complete their cycle. Leavitt made her discovery while working at the Harvard College Observatory, though she was not given an official academic title despite her groundbreaking work. She was one of the Harvard Computers, a group of women hired to perform tedious calculations and measurements on astronomical data. Despite facing significant discrimination, Leavitt's careful analysis of variable stars in the Small Magellanic Cloud led to one of the most important distance measuring tools in astronomy. Her period luminosity relation transformed Cepheid variables from interesting curiosities into powerful standard candles. This discovery was revolutionary because it provided astronomers with a powerful tool. If you could observe a Cepheid variable star through a telescope and carefully measure how long it took to complete its brightness cycle, you could deduce how luminous that star truly was in absolute terms. And once you knew its true luminosity, you could then work out precisely how far away it must be located. You simply compared how bright it appeared in your telescope to how bright you knew it actually was. The dimmer it appeared relative to its true brightness, the farther away it must be located. It was these celestial standard candles that Hubble was methodically searching for in the Andromeda Nebula, and after careful observation, he found them. Buried within the fuzzy, diffuse light of Andromeda were Cepheid variable stars. Hubble patiently measured the regular beating pattern of these stars, recording their brightness over many nights of observation. Once he had gathered enough data, the picture became crystal clear. The mathematics was undeniable. Hubble realized he was observing bright, giant stars located many hundreds of thousands of light years away from Earth. These stars were situated far, far outside the boundaries of the Milky Way galaxy. In 1924, Hubble sent a letter to Harlow Shapley with his findings. The evidence was conclusive. Andromeda was indeed a galaxy in its own right, a vast island universe, just as Heber Curtis had proposed. And if Andromeda was a separate galaxy, then the other spiral nebulae observed through telescopes must also be galaxies, each one home to billions of stars. When Shapley received Hubble's letter, he reportedly exclaimed that it destroyed his universe. Shapley had been wrong about the size of the cosmos, and he knew it. The universe was not confined to the Milky Way. It extended far beyond, filled with countless other galaxies. It was a humbling realization, but it opened up a vastly larger and more interesting cosmos than anyone had previously imagined. The implications were staggering. The universe was not small and confined to the Milky Way. Instead, it was almost incomprehensibly vast, filled with countless galaxies stretching out in all directions. Heber Curtis had been vindicated. The cosmos was far larger than anyone had dared to imagine. But Hubble was not finished. His next discovery would prove even more profound and unsettling. As Hubble continued his observations, examining more and more distant galaxies, he noticed something peculiar. He was measuring not just the distances to these galaxies, but also their motions through space. When light from these distant galaxies passed through a prism, it separated into a spectrum of colours, much like sunlight passing through a raindrop to create a rainbow. Within these spectra were dark lines, absorption features created by specific chemical elements in the stars of those galaxies. The technique of spectroscopy had become one of astronomy's most powerful tools. By studying the patterns of spectral lines, astronomers could determine what elements were present in stars and galaxies. They could measure temperatures and densities, and crucially, they could measure motion. If an object was moving toward or away from Earth, its spectral lines would be shifted in wavelength due to the Doppler effect. Hubble noticed that these spectral lines were shifted toward the red end of the spectrum. This phenomenon is known as redshift, and it occurs when an object is moving away from the observer. It is analogous to the Doppler effect you hear when an ambulance siren drops in pitch as it speeds away from you. The light waves from the receding galaxies are stretched out, shifted toward longer, redder wavelengths. What truly shocked Hubble was the pattern he discovered in his data. The more distant a galaxy was, the faster it appeared to be moving away from us. Nearby galaxies showed small redshifts. Extremely distant galaxies showed enormous redshifts, indicating they were receding at tremendous velocities. This relationship between distance and velocity became known as Hubble's law, and it pointed to an extraordinary conclusion. The universe itself is expanding. Space is stretching, carrying galaxies along with it like raisins in a rising loaf of bread. This was not simply a matter of galaxies moving through space. Space itself is growing larger. The fabric of the cosmos is expanding in all directions, and this expansion has been ongoing for billions of years. This discovery was so radical that even Hubble himself was initially reluctant to fully embrace its implications. An expanding universe suggested that the cosmos had a beginning, a moment of creation. This idea made many scientists uncomfortable because it seemed to border on theology. Some physicists tried to develop alternative explanations, theories where the universe could be expanding yet still be eternal. But the evidence for expansion became overwhelming. The expansion of the universe is often misunderstood. It does not mean that galaxies are flying through space away from each other like shrapnel from an explosion. Instead, space itself is stretching, and galaxies are embedded in that space like points marked on the surface of an inflating balloon. As the balloon expands, the points move farther apart, not because they are moving across the surface, but because the surface itself is growing. This means there is no center to the expansion. Every point in space sees all distant galaxies receding from it. From our perspective, it looks like we're at the center of the expansion, with all galaxies moving away from us. But an observer in any other galaxy would see exactly the same thing. They would see all distant galaxies receding from them. This is because space itself is expanding uniformly in all directions. The rate of expansion is described by the Hubble constant, a number that tells us how fast the universe is expanding. Measuring this constant precisely has been one of the great challenges of modern cosmology. Different methods have given slightly different values, leading to what astronomers call the Hubble tension. This disagreement might point toward new physics, or it might simply reflect uncertainties in the measurements. Resolving this tension is an active area of research. The expansion of the universe was not always steady. In recent decades, astronomers have discovered that the expansion is actually accelerating. Distant galaxies are receding faster and faster over time. This acceleration is attributed to dark energy, a mysterious force that permeates all of space and pushes things apart. The nature of dark energy is one of the biggest unsolved mysteries in physics. Some theories suggest that dark energy might be related to multiverse physics. Perhaps the vacuum energy of our universe, which manifests as dark energy, is just one possible value among many in the string theory landscape. In other bubble universes, the vacuum energy might be different, leading to different expansion histories. Some universes might expand so rapidly that they never form stars. Others might collapse back on themselves before life could evolve. If the universe is expanding now, then it must have been smaller in the past. If you could run time backward like rewinding a film, you would see all the galaxies rushing toward each other. You would see the universe contracting, becoming denser and hotter. Eventually, if you went back far enough, you would arrive at a moment when all of space, all of matter, all of energy was concentrated in an infinitesimally small point of unimaginable density and temperature. This moment is what we now call the Big Bang. It represents the beginning of our universe as we know it, occurring approximately 13.8 billion years ago. From that initial moment of creation, space has been expanding outward, cooling as it grows, allowing matter to form and eventually coalesce into stars and galaxies. This understanding represents one of the most profound discoveries in human history. It tells us that our universe had a definite beginning, and it has a history that we can trace backward through time. The term Big Bang was actually coined by Fred Hoyle, a physicist who was skeptical of the idea. He used it in a somewhat mocking tone during a radio broadcast in 1949. Despite his intentions, the name stuck. Hoyle preferred the steady-state theory, which proposed that the universe had no beginning and was eternally unchanging on cosmic scales. New matter was continuously created to fill the space opened up by expansion. But observation after observation supported the Big Bang model, and the steady-state theory was eventually abandoned by most of the scientific community. The early universe was an extraordinarily different place from the cosmos we see today. In the first fraction of a second after the Big Bang, temperatures were so high that matter as we know it could not exist. The universe was filled with a hot, dense soup of fundamental particles and energy. Quarks and gluons swirled in a plasma too hot for them to combine into protons and neutrons. As the universe expanded and cooled, phase transitions occurred, similar to how steam condenses into water and water freezes into ice. Quarks combined into protons and neutrons. The four fundamental forces, which may have been unified at the highest temperatures, separated into distinct phenomena. The strong nuclear force, the weak nuclear force, electromagnetism, and gravity each took on their distinct identities. About 3 minutes after the Big Bang, when the universe had cooled to about 1 billion degrees, protons and neutrons began to fuse together to form the first atomic nuclei. This process, called Big Bang nucleosynthesis, lasted only a few minutes, but produced the primordial abundances of hydrogen, helium, and trace amounts of lithium and beryllium that we still observe in the oldest stars today. For the next 380,000 years, the universe remained too hot for atoms to form. Any electron that tried to attach to a nucleus would immediately be knocked free by high-energy photons. The universe was opaque, a dense fog of plasma that light could not penetrate. Then, as the temperature dropped below about 3,000 degrees, electrons were finally able to bind to nuclei and form stable atoms. This moment, called recombination, cleared the cosmic fog. Light could suddenly travel freely through space. The light released at recombination is what we now observe as the cosmic microwave background radiation. That ancient light has been traveling through space for nearly 14 billion years, stretched by the expansion of the universe from visible wavelengths into microwaves. When we observe this radiation today, we are seeing a snapshot of the universe as it appeared when it was only 380,000 years old, a cosmic baby picture showing the universe before the first stars formed. The tiny temperature fluctuations in the cosmic microwave background, variations of only about 1 part in 100,000, represent the seeds from which all cosmic structure grew. Regions that were slightly denser than average had slightly stronger gravity. Over millions and billions of years, these density variations grew as matter fell into them, eventually forming galaxies, clusters of galaxies, and the vast filaments and voids we see in the universe today. But this discovery also creates a puzzle, one that leads us directly toward the concept of the multiverse. If the universe began at a specific moment in the past and has been expanding ever since, then there must be a limit to what we can observe. Light travels at a finite speed, about 300 million meters per second. Even though that is extraordinarily fast, it is not instantaneous. Light from distant objects takes time to reach us. Because the universe is only 13.8 billion years old, we can only see objects whose light has had time to reach us since the Big Bang. This creates a cosmic horizon, a boundary beyond which we cannot see, not because those regions do not exist, but simply because light from those regions has not had enough time to travel to Earth. The observable universe has a radius of about 46 billion light-years in every direction. This might seem contradictory, since the universe is only 13.8 billion years old, but it makes sense when you account for the expansion of space itself. The 46 billion light-year radius comes from the fact that, while light was travelling toward us, space itself was expanding. Objects that emitted light 13.8 billion years ago have since been carried away by the expansion of space. They are now much farther than 13.8 billion light-years from us. It is a subtle but important distinction that requires careful thought about the nature of expanding space. The crucial realization is this: the observable universe is not the entire universe. It is only the portion of the universe that we can see from our particular location in space and time. Beyond our cosmic horizon, space continues. Stars and galaxies continue to exist out there, but we will never be able to observe them because their light will never reach us. The universe beyond our horizon is forever hidden from view. This brings us to the first level of the multiverse. Welcome to level 1, the simplest and in some ways the most undeniable version of a multiverse. If space continues beyond what we can observe, if the universe is either infinite or simply much larger than our observable portion, then our cosmic horizon creates, by definition, multiple disconnected regions. Imagine you are standing in a vast, flat desert that stretches to infinity in all directions. Your vision has a limit. You can only see objects within a certain distance. Beyond that distance, the desert continues, but you cannot see it. Now imagine that someone else is standing in that desert, far enough away that you cannot see each other. That person has their own horizon, their own bubble of observable desert around them. Your two horizons might overlap partially, but there are regions you can see that they cannot, and regions they can see that you cannot. This analogy helps us understand the level 1 multiverse, though the reality is more complex. In a desert, you could in principle walk far enough to reach the other person and unite your observable regions. In the cosmos, the expansion of space prevents this. Regions beyond our cosmic horizon are receding from us faster than light can travel. We can never catch up to them, no matter how fast we travel. They are permanently beyond our reach. This is essentially what the level 1 multiverse proposes, except we are talking about the entire universe rather than a desert. If the universe is infinite, or even just extremely large, then there are other regions, other cosmic horizons like ours, each one centered on a different location in space. These other regions would have their own galaxies, their own stars, their own planets. They would be entire universes unto themselves from the perspective of any observer located within them. What makes this idea particularly intriguing is that if the universe is truly infinite, then something remarkable must be true. Given infinite space and a finite number of possible arrangements of matter and energy, every possible configuration must repeat itself eventually. Somewhere out there, far beyond our cosmic horizon, there must be another region that looks exactly like our observable universe. Same galaxies, same stars, same planets, all arranged in precisely the same way. The mathematics behind this is surprisingly straightforward. If you have a finite number of ways to arrange matter in a given volume, and you have infinite volumes of space, then every possible arrangement must occur infinite times. It is like shuffling a deck of cards infinitely many times. Eventually, every possible sequence will appear, and in fact, each sequence will appear infinitely often. The same logic applies to the arrangement of matter and energy in the universe. In fact, if space is truly infinite, there must be infinitely many such regions. There would be infinitely many versions of Earth, infinitely many versions of you, all living out their lives in distant, unreachable corners of the cosmos. Some of these versions would be identical to you in every detail. Others might differ in small ways. Perhaps in one of those distant regions, you chose a different career. In another, you never met your spouse. In yet another, you made a different choice at breakfast this morning. The philosophical implications are profound. If there are infinite copies of you scattered across an infinite universe, what does that mean for personal identity? Are all these copies equally you? Do they share your consciousness somehow? Or is each one a completely independent individual who just happens to be identical? These questions push us into deep philosophical territory about the nature of consciousness and identity. Consider what it means to be you. You have memories, experiences, thoughts, and feelings that seem uniquely yours. But if there is another person in a distant region of space with exactly the same memories, experiences, thoughts, and feelings, are they you or someone else? Most philosophers would say they are someone else, a distinct individual who happens to be your exact duplicate. But this raises puzzling questions about what makes you the particular individual you are. Some philosophers argue that personal identity depends on continuity of consciousness over time. You are the same person you were yesterday, because there is a continuous thread of consciousness connecting your present self to your past self. By this logic, your duplicates in distant regions of space are not you, because there is no continuity of consciousness between you and them. They are separate consciousnesses that emerged independently. But the level 1 multiverse raises another question. If your duplicates are living out lives identical to yours, experiencing the same thoughts and feelings at the same moments, is there really any meaningful difference between you and them? From your subjective perspective, you would never know which copy you are. The experience would be identical. This leads some philosophers to wonder whether personal identity might be more fluid and less absolute than we typically assume. These questions become even more complex when we consider the level 3 multiverse, where every quantum measurement causes you to split into multiple versions. In that case, there is continuity of consciousness between you and your branching copies. They all emerged from the same original you. Are they all equally you? Do you somehow experience all the branches simultaneously? The answers remain deeply uncertain. This is not science fiction. This is a genuine consequence of basic cosmology combined with the assumption that the universe is infinite. Of course, we do not know for certain whether the universe is truly infinite. It might simply be extremely large, but still finite. Current observations suggest the universe is flat, which would imply infinite extent, but our measurements are not precise enough to be absolutely certain. The level 1 multiverse arises simply from the size and structure of space itself, but there are other types of multiverses that emerge from different aspects of physics. The second level of multiverse comes from a particular theory about how the universe evolved in its earliest moments. This brings us to the concept of cosmic inflation. In the early 1980s, physicist Alan Guth proposed a radical solution to several problems in cosmology. He suggested that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion. During this inflationary period, space expanded exponentially, doubling in size over and over again in an incredibly brief span of time. This inflation happened so quickly that regions of space that started out in contact with each other were suddenly separated by enormous distances. Guth was working on problems related to particle physics and the early universe when he made his breakthrough. One puzzle that had troubled cosmologists was the horizon problem. How could the universe be so uniform in all directions if different regions had never been in contact with each other? Inflation provided an elegant answer. Before inflation, the entire observable universe was compressed into a tiny region where everything was in thermal contact. Then inflation stretched this tiny region to enormous size, maintaining the uniformity. Another problem inflation solved was the flatness problem. Observations showed that the geometry of space is remarkably flat, neither curving back on itself like a sphere, nor curving outward like a saddle. But flatness is an unstable condition in general relativity. Any tiny deviation from perfect flatness in the early universe should have grown larger over time. The fact that space is still nearly flat today, billions of years later, seemed to require extraordinarily precise fine-tuning of initial conditions. Inflation solved this by stretching space so dramatically that any initial curvature was smoothed out, like wrinkles on a balloon that disappear as the balloon is inflated. Inflation also explained the origin of structure in the universe. Quantum fluctuations in the inflating field would be stretched to cosmic scales, creating tiny density variations. These variations would later grow into galaxies and galaxy clusters. This prediction was spectacularly confirmed by observations of the cosmic microwave background, which showed exactly the pattern of fluctuations predicted by inflation. When Guth first proposed inflation, it was met with considerable skepticism. The idea required a special type of field, called the inflaton field, that had never been observed. It also required very specific properties to make inflation start and stop at the right times. Many physicists doubted whether such a field could really exist. But as evidence accumulated, and the theory was refined by Guth, André Linde, Paul Steinhardt, and others, inflation became widely accepted as the best explanation for the early universe. The inflationary paradigm has been tested in many ways. The temperature fluctuations in the cosmic microwave background match inflation's predictions to high precision. The flatness of space aligns with inflation's expectations. The absence of magnetic monopoles, exotic particles predicted by particle physics that should have been produced in the early universe but have never been found, is naturally explained by inflation diluting them to undetectable densities. However, inflation is not without its critics. Some physicists, including Paul Steinhardt, who helped develop the theory, have become skeptical of eternal inflation and the multiverse it implies. They argue that a theory that predicts everything and anything loses its explanatory power. If every possible universe exists somewhere in the multiverse, then we can never explain why our universe has the specific properties we observe. The anthropic principle becomes a crutch that allows us to avoid finding deeper explanations. Inflation solves several cosmological puzzles quite elegantly. It explains why the universe appears so uniform in all directions. It explains the precise flatness of space. But inflation also creates something unexpected. Most versions of inflation theory are eternal. Once inflation begins in one region, quantum fluctuations ensure that it never completely stops everywhere at once. Instead, inflation ends in some regions, creating what we call bubble universes, while continuing in other regions. The mechanism behind eternal inflation is fascinating. Quantum mechanics tells us that even in empty space, fields can fluctuate randomly. In most places, These fluctuations cause inflation to end, but in some places, the fluctuations cause inflation to continue. Those regions where inflation continues keep expanding, creating more volume, which in turn creates more opportunities for both inflation to end and to continue. The process becomes self-perpetuating. It can never truly stop everywhere at once. Imagine a vast ocean where bubbles are constantly forming. Each bubble is a universe like our own, a region where inflation has ended and normal expansion has taken over. But the space between the bubbles continues to inflate eternally, creating more volume, spawning more bubbles. This process never stops. It has been going on forever into the past, and it will continue forever into the future, generating an infinite number of bubble universes. This is the level 2 multiverse. Each bubble universe has its own properties. The laws of physics might differ from one bubble to another. The values of fundamental constants, like the strength of gravity or the mass of an electron, might vary. Some bubble universes might be hospitable to life. Others might be completely barren, unable to form stars or planets or any complex structures. Our universe, our bubble, happens to have properties that allow for the existence of atoms, stars, planets, and ultimately life. But we may simply be one bubble among an infinite sea of bubbles, each one a separate universe with its own unique characteristics. The level 2 multiverse suggests that the fundamental laws and constants we observe are not unique. They are merely one possibility among countless others. The concept of eternal inflation is scientifically respectable. It is based on well-established physics and makes testable predictions about the early universe. Many cosmologists take it seriously as a potential explanation for the state of our cosmos. But if eternal inflation is true, then the level 2 multiverse may be an unavoidable consequence. We cannot see these other bubble universes because they are separated from us by regions of still inflating space, regions that are expanding so rapidly that light can never traverse them. String theory adds another layer of complexity to the level 2 multiverse. String theory proposes that the fundamental constituents of reality are not point particles, but tiny, vibrating strings of energy. Different vibration patterns of these strings correspond to different particles. An electron is one vibration pattern. A quark is another. A photon is yet another. String theory emerged in the 1960s and 70s as physicists searched for a way to unify quantum mechanics with general relativity. At very small scales and high energies, particles can no longer be treated as simple points. They must be thought of as tiny, extended objects. The mathematics of string theory is extraordinarily complex, requiring advanced techniques from pure mathematics that were not originally developed with physics in mind. The history of string theory is filled with unexpected twists and remarkable mathematical discoveries. It began as an attempt to understand the strong nuclear force, but was abandoned when quantum chromodynamics proved more successful for that purpose. Then physicists realized that string theory naturally included gravity, something no other quantum theory had achieved. Suddenly, string theory was reborn as a potential theory of everything, a framework that could unify all forces and particles. In the 1990s, string theorists made a series of breakthroughs that transformed the field. They discovered that different versions of string theory were all connected through mathematical relationships called dualities. What appeared to be 5 distinct string theories were actually 5 different ways of looking at the same underlying theory. This led to the development of M-theory, a more comprehensive framework that includes all 5 string theories as special cases. M-theory introduced the concept of branes, higher dimensional objects that generalize the idea of strings. A one-dimensional string is a one brane. A two-dimensional membrane is a two-brane. In M theory, our entire three-dimensional universe might be a three-brain floating in a higher dimensional space. Other brains could exist nearby in the extra dimensions, perhaps representing other universes parallel to our own. Some versions of string theory suggest that our universe and others could be brains in a higher dimensional bulk space. Gravity might be able to leak between brains, while other forces remain confined to individual brains. This could explain why gravity is so much weaker than the other forces. Most of the gravitational force might be spreading out into extra dimensions, while other forces are trapped on our brain. Despite its mathematical beauty, string theory faces significant challenges. It makes few testable predictions at energies we can achieve in particle accelerators. The theory requires extra dimensions, but these dimensions are so small that detecting them directly seems impossible with current technology. Critics argue that string theory has become more mathematics than physics, producing elegant equations but few connections to observable reality. The string theory landscape, with its 10 to the power of 500 possible vacuum states, is both a feature and a bug. It provides a potential explanation for why our universe has the specific properties it does through the anthropic principle. But it also means the theory lacks predictive power. If almost anything is possible within the landscape, how can we use string theory to make definite predictions about what we should observe? String theorists are working to address these challenges. Some are searching for universal predictions that hold across the entire landscape. Others are trying to find principles that might select out a smaller subset of possibilities. Still others are developing new mathematical tools to better understand the theory's structure. The work is slow and difficult, but many physicists believe string theory remains our best hope for a complete theory of quantum gravity. String theory is mathematically elegant and has the potential to unify all the forces of nature into a single framework. But it comes with some unusual requirements. For the mathematics to work properly, string theory requires extra dimensions of space beyond the three we experience. Depending on the specific version of string theory, there might be 6 or 7 additional dimensions, bringing the total number of spatial dimensions to 9 or 10. These extra dimensions are thought to be compactified, meaning they are curled up so tightly that we cannot perceive them directly. Imagine an ant walking along a tightrope. From the ant's perspective, it can move forward and backward along the rope, but the rope also has a tiny circular dimension around its circumference. If that circular dimension is small enough, the ant might not even realize it exists. Similarly, the extra dimensions in string theory might be real, but simply too small for us to detect. The scale of these compactified dimensions would be unimaginably small, perhaps on the order of the Planck length, about 10 to the power of minus 35 meters. That is a billion times smaller than an atomic nucleus. At the energies we can achieve in particle accelerators, we cannot probe such tiny distances. The extra dimensions remain hidden, affecting physics only in subtle ways that are difficult to detect. The critical point is this: there are many different ways these extra dimensions can be compactified. Each different configuration would result in different physical laws and constants in the resulting three-dimensional universe. String theorists have calculated that there might be 10 to the power of 500 different possible configurations, a number so staggeringly large it defies comprehension. This vast landscape of possibilities is called the string theory landscape. To put 10 to the power of 500 in perspective, consider that there are perhaps 10 to the power of 80 atoms in the observable universe. There are maybe 10 to the power of 20 stars in the observable universe. 10 to the power of 500 is incomparably larger. It is a 1 followed by 500 zeros. The string theory landscape contains more possible universes than there are atoms, stars, or anything else we can physically count. If eternal inflation is combined with the string theory landscape, the result is truly mind-boggling. Each bubble universe created by eternal inflation might crystallize with a different configuration of extra dimensions. This means there could be 10 to the power of 500 different types of bubble universes, each with its own unique laws of physics. Our universe would be just one incredibly unlikely lucky combination that happens to allow for our existence. This idea helps address a puzzle called the fine-tuning problem. The constants of nature in our universe appear to be exquisitely calibrated to allow for life. If gravity were slightly stronger or weaker, if the electron mass were different by even a small amount, stars could not form, or atoms would not be stable, or chemistry as we know it would be impossible. Why does our universe have precisely the right properties for life? One answer is the anthropic principle combined with the multiverse. If there are countless bubble universes with different properties, then we should not be surprised to find ourselves in one of the rare bubbles where life is possible. We could not exist in any of the other bubbles, so naturally we observe a universe that supports our existence. It is a selection effect, not a miracle. The anthropic principle is sometimes seen as a cop-out, a way of avoiding the hard work of finding deeper explanations. But if the multiverse is real, the anthropic principle may be an unavoidable part of our theoretical framework. We can only observe universes that are capable of producing observers. This is a selection bias, but it is a real and important one that must be taken into account. But we are not done yet. There is a third type of multiverse, one that emerges not from cosmology, but from the deepest foundations of quantum mechanics itself. This is perhaps the strangest and most philosophically challenging of all multiverse ideas. This is the many worlds interpretation of quantum mechanics. To understand the many worlds interpretation, we must first appreciate just how strange quantum mechanics truly is. The quantum world defies our everyday intuitions about reality. Objects at the quantum scale behave in ways that seem impossible according to classical physics. They can exist in multiple states simultaneously. They can influence each other instantaneously across vast distances. They can tunnel through barriers that should be impenetrable. These bizarre quantum effects are not merely theoretical curiosities. They have been confirmed in countless experiments over the past century. The entire modern world depends on quantum mechanics. Computers, smartphones, lasers, and medical imaging devices all rely on quantum principles. Yet despite its practical success, quantum mechanics presents us with profound conceptual puzzles that remain unresolved. One of the deepest puzzles is the measurement problem. Before a quantum system is measured, it exists in a superposition of multiple states. An electron can be spinning both up and down simultaneously. A photon can be in multiple locations at once. But when we measure the system, we always find it in one definite state. The superposition seems to collapse into a single outcome. What causes this collapse? Does measurement force reality to choose between possibilities, or is something more subtle happening? Different interpretations of quantum mechanics offer different answers to these questions. And the many worlds interpretation provides one of the most radical solutions. In the early 20th century, physicists discovered that the subatomic world behaves in ways that are fundamentally different from our everyday experience. Particles like electrons do not have definite positions and velocities. Instead, they exist in what is called a superposition, a strange quantum state where they are in multiple states simultaneously until they are observed or measured. The transition from classical physics to quantum mechanics was one of the most dramatic revolutions in the history of science. Classical physics, the physics of Newton and Maxwell, describes a deterministic world where knowing the present state of a system allows you to predict its future exactly. Quantum mechanics destroyed this determinism, replacing it with probabilities and uncertainties that are built into the fabric of reality itself. The famous double-slit experiment demonstrates this bizarre behavior. When you fire electrons one at a time toward a barrier with two narrow slits, something strange happens. Each electron somehow passes through both slits at the same time and interferes with itself, creating an interference pattern on a detector screen. This only makes sense if each individual electron is in a superposition, existing in a state where it went through both slits simultaneously. The double-slit experiment has been performed with electrons, photons, atoms, and even molecules. The result is always the same. Individual quantum particles behave like waves, interfering with themselves, existing in superpositions of multiple states. It is one of the most well-established yet most perplexing phenomena in all of physics. But here is where things get really weird. If you place a detector at the slits to observe which path each electron takes, the interference pattern disappears. The act of measurement seems to force the electron to choose one path or the other. Before measurement, it was in a superposition. After measurement, it has a definite state. This is called the collapse of the wave function. The question is, what actually happens during this collapse? The standard interpretation, called the Copenhagen interpretation, essentially says that the wave function collapse is a real physical process. Measurement causes reality to crystallize from multiple possibilities into a single actuality. But this raises troubling questions. What counts as a measurement? Does it require a conscious observer? How does nature decide which outcome to choose? The Copenhagen interpretation was developed primarily by Niels Bohr and Werner Heisenberg in the 1920s. It dominated physics for decades, partly because it worked practically. Physicists could calculate probabilities and make predictions without worrying too much about the philosophical implications. But as quantum mechanics matured, some physicists became increasingly dissatisfied with this shut up and calculate approach. They wanted to understand what was really happening. In 1957, a graduate student named Hugh Everett proposed a radical alternative. What if the wave function never collapses at all? What if instead, when a quantum measurement occurs, reality itself splits into multiple branches? In one branch, the electron went through the left slit. In another branch, it went through the right slit. Both outcomes happen, but in different parallel universes that can no longer interact with each other. This is the many worlds interpretation. It proposes that every quantum event causes the universe to branch into multiple copies, one for each possible outcome. When you flip a coin, the universe splits into two branches. In one branch, the coin comes up heads. In another branch, it comes up tails. Both outcomes are equally real, but they exist in separate, parallel worlds. The implications are staggering. Every quantum event everywhere in the universe is constantly causing reality to branch. The number of parallel worlds is growing exponentially with each passing moment. There are versions of you in countless parallel universes, living out every possible variation of your life based on different quantum outcomes. This is the Level 3 multiverse. It differs from the Level 1 and Level 2 multiverses in an important way. Those earlier multiverses involve different regions of space, either beyond our horizon or in separate bubble universes. The level 3 multiverse involves copies of the same space, branching into parallel quantum realities that somehow coexist alongside our own. Many physicists find the many worlds interpretation deeply troubling. It seems extravagant, even wasteful, to propose that reality is constantly splitting into an ever-growing tree of parallel worlds. Nobel Prize winner Gerard Hooft criticized the idea, calling it a stupendous number of parallel worlds which exist only because physicists could not decide which of them is real. Hugh Everett himself faced considerable resistance during his lifetime. After receiving a cold reception from much of the physics community, including Niels Bohr himself, Everett left physics after completing his doctorate. He went on to work as a computer programmer and died of a heart attack at the age of just 51. His revolutionary ideas were largely ignored for decades. Everett's life story is somewhat tragic. He developed his many worlds interpretation as a young man, convinced he had solved one of the deepest problems in physics. But the physics establishment rejected his ideas, and he spent most of his adult life working in defense-related computer science, far from the academic world of physics. Only near the end of his life did a new generation of physicists begin to take his ideas seriously. But in recent years, there has been a resurgence of interest in many worlds. A new generation of physicists has begun to take the interpretation seriously. To some researchers, many worlds represents the only realistic solution to the measurement problem in quantum mechanics. It is the only way to truly follow the mathematics without adding extra assumptions about wave function collapse. The equations of quantum mechanics naturally describe branching, and many worlds simply takes those equations seriously. There are still deep questions that many worlds does not answer. What happens to consciousness when the universe branches? If the universe splits into two branches where you made different choices, are there now two distinct versions of you? Do they both feel like the continuous you? Each version would have the memories and experiences from before the split, but then their experiences would diverge. How does subjective experience relate to this branching of worlds? These are questions that philosophers love to explore. There is a thought experiment that illustrates the strangeness of many worlds quite vividly. It is called quantum immortality or quantum suicide, though the names make it sound more dramatic than it is. Imagine you have a perfectly fair coin with equal chances of coming up heads or tails. The stakes on flipping this coin are very high. If it comes up tails, you will be executed. If it comes up heads, you survive. As the coin spins in the air, you know the outcome is 50-50. In the Copenhagen interpretation, when the coin lands, one outcome occurs, and that is your reality. If it comes up tails, your story ends. If it comes up heads, you continue on. In many worlds, however, something different happens. The universe splits. In one branch, the coin came up heads, and you survived. In another branch, the coin came up tails, and you were executed. Now imagine you are instructed to flip the coin again, and again, and again. In the Copenhagen interpretation, this is a game you are bound to lose eventually. You would have to be extraordinarily lucky to keep getting heads on every single flip. Your execution seems inevitable, but in the many worlds interpretation, something curious occurs. With each flip, the universe continues to split. After the first flip, there are two branches, one where you survived and one where you died. After the second flip of the coin in the survival branch, there are now 4 total branches, one where you survived twice, 2 where you died on either the first or second flip, and so on. As the coin is flipped repeatedly, the number of branches multiplies exponentially. Most branches lead to your death at some point, but there is always at least one branch one future history where you continue to survive against all odds. The question is, what would you experience if you were the coin flipper? Would you find yourself on the lucky path where you survive indefinitely? The answer depends on deep questions about consciousness that nobody fully understands. Some versions of many worlds suggest that your subjective experience would always continue along a surviving branch, because in the branches where you die, there is no longer any you to experience anything. This leads to the strange conclusion that from your subjective perspective, you might seem to be immortal, always finding yourself in the improbable surviving branch. It must be emphasized that this thought experiment is not a practical suicide method. The experiment assumes a truly quantum device that creates perfect superposition, and it relies on highly speculative claims about consciousness and identity that are far from proven. But it does illustrate the bizarre implications of taking many worlds seriously. If reality is constantly branching, what does that mean for continuity of consciousness and personal identity? This thought experiment raises profound philosophical questions, but it also illustrates just how strange the many worlds interpretation truly is. It forces us to reconsider the nature of probability, identity, and existence itself. You might think at this point that we have reached the end of our exploration of multiverse concepts. What could possibly contain more than the ultimate quantum superposition of all possible universes? To arrive at this point, we have already abandoned our usual understanding of reality. We have considered parallel worlds beyond our cosmic horizon. We have contemplated vast, nested infinities stretching out beyond eternity. But there is one more step, one final level of multiverse that pushes speculation to its absolute limit. To understand the level 4 multiverse, we must let go completely and utterly of any conventional notion of physical reality. We must ask the most fundamental question of all. What is reality itself? As you look around you right now, reality seems obvious. You are surrounded by stuff. Some of it is solid, like a table or a wall. Some of it is liquid, like water. Some of it is as ethereal and invisible as the air you are breathing. But you should know by now that this apparent reality is itself an illusion. If you could zoom in and examine matter closely enough, you would see that everything is made of atoms. These atoms combine in various ways to form different molecules, which give rise to the different materials and substances we experience. But we can strip back reality even further. Atoms themselves are not fundamental. They can be dismantled into smaller pieces. An atom consists of a nucleus made of protons and neutrons, surrounded by a cloud of electrons. But even protons and neutrons are not fundamental. They are made of even smaller particles called quarks, held together by particles called gluons. Do these fundamental particles, these quarks and electrons and photons, represent the purest, most basic form of reality? Not quite. To fully describe reality, we also need to include the ways these particles interact with each other through the fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. And how do we describe all of this? We describe it using the language of mathematics. Mathematics provides us with numbers and equations that precisely describe how reality behaves. The laws of physics are written in mathematical language. But this raises a profound question. Where do these mathematical rules exist? Where do the laws of physics actually live? This might seem like a very strange question at first. These laws seem abstract, like concepts that exist in our minds or in textbooks. But if mathematics describes reality so perfectly, perhaps mathematics is reality. This brings us to Max Tegmark's Level 4 multiverse, the most speculative and philosophically radical multiverse of all. The Level 4 multiverse proposes that reality is nothing more than mathematics itself. Not that reality can be described by mathematics, but that reality is mathematics. Our universe, with all its particles and forces and structures, is simply one mathematical structure among countless others. In the Level 4 multiverse, every possible mathematical structure exists in some sense. These mathematical structures encompass the entire realm of logical possibility. Some of these structures would correspond to universes like our own. Others might have completely different rules, different types of particles, different numbers of dimensions, different fundamental forces. Some mathematical structures might not look like universes at all in any way we would recognize. All the other types of multiverse we have discussed, the Level 1, Level 2, and Level 3 multiverses, would be contained within this Level 4 multiverse. They would all be different mathematical structures or different parts of the same mathematical structure. The Level 4 multiverse is the ultimate ensemble, the complete collection of every possible kind of reality and much, much more. This idea bears some similarity to the simulation hypothesis that has become popular in recent years. The simulation hypothesis proposes that our reality might be nothing more than an extremely sophisticated computer program running on some vast computer. That computer would exist in another universe, a parent universe, and our reality would be a simulation created by beings in that higher reality. We would be nothing more than characters in their program, digital entities to whom they are like gods. But the Level 4 multiverse that Max Tegmark proposes would be even more fundamental than a physical computer simulation. It would not require any physical computer at all. It would be pure existence of mathematics itself, with no underlying physical substrate needed. Mathematical structures would simply exist by virtue of being logically possible. We have now arrived at the very edge of speculation. After climbing through layer after layer of multiverse ideas, we have reached the ultimate view. We began our journey by simply peering over our cosmic horizon and wondering what might lie beyond. We wondered what existed in regions of space too distant for light to have reached us yet. Now we find ourselves questioning the very meaning and nature of reality itself. We are asking whether existence is fundamentally mathematical, whether physical reality emerges from abstract logical structures. What has become clear through this exploration is that the multiverse is not one single concept. It is not one simple idea. Rather, it is a collection of related but distinct proposals, a grab bag of ideas ranging from the scientifically well-established to the frankly speculative. Some of these ideas are built on solid theoretical physics and observational evidence. Others venture into territory that is closer to philosophy or even science fiction. Before we conclude this exploration, a word of caution is necessary. Discussions about the multiverse in public forums and even in academic settings often become heated. They can devolve into shouting matches between proponents and skeptics. This happens because the stakes feel very high. The multiverse challenges our fundamental understanding of reality and the nature of scientific inquiry itself. For some physicists, the existence of some form of multiverse seems almost inevitable. Ideas like eternal inflation are simply too compelling and too well grounded in established physics to dismiss. These physicists argue that we must follow the mathematics wherever it leads, even if that means accepting the existence of regions or realities beyond our ability to observe directly. Other aspects of the multiverse, like the string theory landscape, emerge naturally from theoretical frameworks that many physicists believe are on the right track toward a complete theory of nature. Even the seemingly modest idea of wondering what lies beyond our cosmic horizon implies a kind of multiverse by definition. If the universe extends beyond what we can see, then there are regions that function as separate universes from our perspective. To these researchers, denying the possibility of a multiverse seems like denying obvious logical consequences of well-established science. But other physicists vehemently oppose the entire notion of a multiverse. To them, talking about universes or realities that are forever beyond our reach is fundamentally unscientific. They argue that ideas are only truly scientific if they can be tested through observation or experiment. If parallel universes will never be visible through our telescopes or accessible through our particle accelerators, if they are in principle beyond any form of scientific scrutiny, then they should not be considered part of science at all. They should be relegated to philosophy or metaphysics. These skeptics worry that accepting untestable multiverse theories will weaken the foundations of science. They fear it will allow physicists to give up on finding testable explanations for observations and instead invoke unobservable parallel worlds as explanations for anything we do not understand. They see the multiverse as a dangerous retreat from the rigorous standards that have made science so successful. In truth, neither side in this debate holds the complete scientific high ground. The reality is more nuanced than either extreme position suggests. Our multiverse theories are simply too early in their development for us to judge their ultimate scientific validity with any certainty. Some of the foundational mathematics might be firmly in place, but enormous mysteries still remain to be solved. Questions about how individual bubble universes crystallize out of eternally inflating space remain unanswered. We do not fully understand the dynamics of eternal inflation or what determines the properties of each bubble. String theory remains hugely popular among theoretical physicists and has produced many beautiful mathematical insights, but it still lacks definitive experimental proof. No one has yet detected the extra dimensions or the supersymmetric particles that many versions of string theory predict must exist. The many worlds interpretation of quantum mechanics has passionate and articulate defenders, but it remains just one interpretation among several. Other interpretations of quantum mechanics make identical predictions for all observable phenomena. The scientific evidence we have cannot yet definitively distinguish between many worlds and alternatives like the Copenhagen interpretation or pilot wave theory. The choice between these interpretations comes down to philosophical preferences about simplicity, elegance, and the nature of reality. And Max Tegmark's mathematical universe hypothesis, his level 4 multiverse of all possible mathematical structures, remains little more than a philosophical dream at this stage. It is a fascinating idea to contemplate, but it is not clear how it could ever be tested or verified through scientific methods. Tegmark's proposal rests on a bold claim about the nature of mathematics itself. Most people think of mathematics as a human invention, a language we created to describe patterns in nature. But Tegmark suggests that mathematics is not invented but discovered. Mathematical truths exist independently of human minds. The Pythagorean theorem was true before humans discovered it, and it will remain true even if humanity disappears. If mathematics exists independently, then perhaps all mathematically consistent structures exist in some fundamental sense. This leads to a dizzying conclusion. Every possible universe that can be described mathematically actually exists somewhere in the level 4 multiverse. Our universe, with its specific laws and constants, is just one mathematical structure among an infinite variety. There could be universes with different numbers of dimensions, different particles, different forces, or even different logical structures underlying reality itself. Some of these mathematical universes might be utterly alien to anything we can imagine. They might not have space or time as we understand them. They might not have causality or any recognizable physical laws. They would be pure, abstract structures, existing in the realm of mathematical possibility. Yet, according to Tegmark, they would be just as real as our own universe, simply existing as different mathematical objects. The philosophical implications are staggering. If the Level 4 multiverse is real, then everything that can exist does exist. Every story that can be told, every pattern that can be formed, every possibility that can be imagined exists somewhere in mathematical reality. We are just one brief pattern in an infinite tapestry of mathematical structures. Critics argue that Tegmark's proposal is unfalsifiable and therefore unscientific. If every possible universe exists, then any observation can be explained by saying we happen to live in the universe where that observation occurs. There is no way to test or disprove the theory. Defenders counter that the mathematical universe hypothesis makes some predictions, such as the existence of a multiverse and the applicability of anthropic reasoning, though these predictions are admittedly difficult to test directly. The debate about Tegmark's Level 4 multiverse touches on fundamental questions about the nature of existence and mathematics. Is mathematics something we invent or something we discover? Do abstract mathematical objects exist in some Platonic realm? Can something be real if it exists only as a mathematical structure with no physical instantiation? These questions have puzzled philosophers for millennia, and they remain unresolved today. None of this means that the multiverse concept will necessarily remain forever beyond the reach of science. With enough mathematical development and theoretical progress, we might eventually find a way to peek into parallel realities. We might discover complex structures in space-time, something analogous to the concept of wormholes that could bring the seemingly unseeable into view. Perhaps there are pathways between bubble universes that could be traversed or at least observed. Some researchers have suggested that evidence of the multiverse might already be written in the sky, encoded in subtle patterns in the cosmic microwave background radiation. The cosmic microwave background is the faint afterglow of the Big Bang, radiation that has been traveling through space for nearly 14 billion years. It shows us what the universe looked like when it was only 380,000 years old, long before the first stars formed. Some physicists have proposed that if our bubble universe collided with another bubble universe in the distant past, such a collision might have left a distinctive signature in the cosmic microwave background. It might appear as a circular pattern, a bruise on the sky marking where the two bubble universes touched. So far, searches for such patterns have not revealed any definitive evidence, but the search continues. The cosmic microwave background might also provide clues about whether our universe is spatially flat or curved. If the universe is perfectly flat, as current measurements suggest, then it is likely infinite in extent. This would strengthen the case for the Level 1 multiverse, the idea that there are other observable regions beyond our cosmic horizon. If measurements reveal even a tiny curvature, it might indicate that the universe is finite, wrapping back on itself in some higher dimensional space. This would not rule out other types of multiverse, but it would eliminate the simplest form. The search for evidence continues on multiple fronts. Physicists are looking for anomalies in particle physics experiments that might point toward extra dimensions or unexpected particle species. Cosmologists are analyzing the distribution of galaxies and the properties of dark matter and dark energy, searching for clues about the underlying structure of reality. Theorists are working to develop more complete and testable versions of string theory and eternal inflation. The Large Hadron Collider, the most powerful particle accelerator ever built, has been smashing protons together at unprecedented energies. Scientists hoped it might reveal signs of extra dimensions or supersymmetric particles predicted by string theory. So far, these exotic phenomena have not appeared, but the search continues. Each negative result helps constrain the possibilities and refine our theories. Dark matter and dark energy present their own mysteries that might connect to multiverse theories. Dark matter makes up about 27% of the universe, yet we have never directly detected a dark matter particle. Dark energy, which drives the accelerating expansion of the universe, makes up about 68% of the universe, yet we have no idea what it is. Some theories suggest that the properties of dark matter and dark energy might be explained by interactions with other universes or extra dimensions. Gravitational wave astronomy, a new field opened by the first detection of gravitational waves in 2015, offers another potential window into the multiverse. These ripples in space-time, caused by colliding black holes and neutron stars, carry information about the structure of the universe. Some theorists have proposed that gravitational waves might be affected by extra dimensions or could even propagate between bubble universes. Quantum computing represents another frontier where multiverse ideas intersect with practical technology. Quantum computers exploit superposition to perform certain calculations exponentially faster than classical computers. Some interpretations suggest that quantum computers are somehow accessing the computational power of parallel universes. While this is highly speculative, it illustrates how multiverse thinking permeates modern physics. Advances in cosmological observations continue to refine our understanding of the early universe. The Planck satellite mapped the cosmic microwave background with unprecedented precision. Future missions may detect primordial gravitational waves, ripples from the inflationary epoch that could provide direct evidence for inflation and potentially hint at the existence of other bubble universes. Theoretical physicists are also exploring new mathematical frameworks that might make multiverse theories more testable. Some approaches involve finding universal predictions that hold across all possible universes in the multiverse. Others search for statistical patterns that could distinguish between single universe and multiverse scenarios. While progress is slow, the work continues. For now, however, any form of direct contact with or concrete evidence for these alternate realities remains purely wishful thinking. We have no confirmed observations of other universes. We have no verified theories that definitively require a multiverse. We simply have compelling theoretical frameworks that seem to point in that direction, combined with a lot of unanswered questions. In reality, the multiverse may indeed be forever hidden within a fog that we can never fully penetrate. Like Edward Quinn's clouds of ignorance on his historical atlas, there may be limits to what we can ever know about reality. Some clouds may never be fully dispersed, but that has never stopped human curiosity before, and it will not stop it now. Scientists will continue to push at the boundaries of knowledge, peering as far into the fog as their tools and theories will allow. The concept of the multiverse, in all its various forms, represents humanity's current best attempt to grapple with profound questions about existence. Why does the universe have the properties it does? Why is there something rather than nothing? Are we alone? Not just in our universe, but in all of reality. These are questions that have occupied philosophers and theologians for millennia. Now they occupy physicists as well. The question of why there is something rather than nothing is perhaps the deepest mystery of all. The multiverse, particularly the level 4 mathematical multiverse, offers one possible answer. If all mathematically consistent structures must exist, then the question becomes not why is there something, but how could there be nothing? Nothingness itself might be impossible because even the concept of nothing is a mathematical structure. But this answer simply pushes the mystery back one level. Why do mathematical structures exist? Why is mathematics able to describe reality so perfectly? These questions lead us to the edge of what science can address. We find ourselves in the territory traditionally occupied by philosophy and theology, where different worldviews offer different answers and evidence becomes scarce. The multiverse also raises questions about meaning and purpose. If every possible outcome occurs in some branch of the multiverse, does that make our choices meaningless? If there are versions of you making every possible decision, does it matter which version you happen to be? Most philosophers would argue that it does matter. Your choices still determine which particular path through the branching multiverse you experience. The existence of other versions of you making different choices does not diminish the reality or importance of the choices you make. Some find the multiverse concept liberating. It suggests that reality is far richer and more diverse than we ever imagined. Every possibility, every potential universe, every imaginable configuration of matter and energy might exist somewhere. There is something almost hopeful in that idea, a sense that reality is boundlessly creative and generative. Others find the multiverse deeply troubling or even depressing. If everything that can happen does happen somewhere, it might seem to rob our universe of uniqueness or specialness. If we are just one bubble among infinite bubbles, one branch among infinite branches, one mathematical structure among infinite structures, does that diminish our significance? Perhaps the answer depends on perspective. On one level, yes, we are just a tiny part of an incomprehensibly vast multiverse, if the multiverse exists. But on another level, our existence, our consciousness, our ability to ask these questions and seek answers remains remarkable regardless of what exists beyond our cosmic horizon. The fact that we can contemplate the multiverse, that we can use mathematics and observations to peer into its possible structure, is itself extraordinary. The multiverse also offers a different perspective on the fine-tuning problem. Instead of seeing our universe's life-permitting properties as evidence of design or purpose, we can see them as a selection effect in a vast landscape of possibilities. This does not necessarily make our existence less meaningful. It simply locates the explanation in natural processes rather than in purpose or intention. Some theologians and philosophers have argued that the multiverse and theism are not necessarily in conflict. If a deity exists and chooses to create not just one universe, but many or infinite universes, exploring every possibility that could be seen as an expression of infinite creativity, the multiverse, in this view, would be part of the divine creation, not an alternative to it. These ideas show how multiverse theories intersect with ancient questions about the nature of existence and our place within it. Whether the multiverse turns out to be real or merely an interesting intellectual exercise, the journey of exploration has value. It pushes us to think more clearly about the foundations of physics. It forces us to confront the limits of scientific knowledge. It challenges our assumptions about what is real and what can be known. Even if we never find definitive evidence for parallel universes, the attempt to understand them will likely lead to unexpected discoveries and insights. The history of science is filled with examples where pursuing seemingly impossible ideas led to profound breakthroughs. When Albert Einstein proposed that time and space were relative rather than absolute, many scientists thought the idea was absurd. When Werner Heisenberg suggested that particles do not have definite properties until they are measured, it seemed to violate basic logic. When Georges Lemaitre proposed that the universe had a beginning, it appeared to mix science with theology. Yet all these ideas, once considered radical or even nonsensical, are now fundamental to our understanding of reality. The multiverse might follow a similar path. What seems speculative or untestable today might become mainstream science tomorrow. New technologies, new mathematical techniques, and new ways of thinking could open doors that currently seem permanently closed. Or we might discover that the multiverse is fundamentally beyond our reach, but in the process of searching for it, we might uncover other profound truths about the nature of reality. The scientific method itself has evolved over time. Early natural philosophers relied primarily on logical reasoning and direct observation. The scientific revolution introduced controlled experiments and mathematical modeling. The 20th century added statistical methods and increasingly sophisticated instruments. The 21st century might require new epistemological frameworks to tackle questions like the multiverse, approaches that blend rigorous mathematics with careful philosophical reasoning. Some philosophers of science argue that testability is not the only criterion for good science. Theories can be valuable if they provide coherent explanations, make logical sense, fit with other well-established theories, and offer new insights, even if they cannot be directly tested. By these broader criteria, multiverse theories might have scientific merit, even if we can never directly observe other universes. Others maintain that without testability, we have left the realm of science and entered the realm of metaphysics. They worry that accepting untestable theories opens the door to all sorts of speculation disconnected from empirical reality. The debate continues, and it reflects deeper questions about the nature and limits of scientific knowledge itself. Science has always progressed by asking seemingly impossible questions and then stubbornly working toward answers. A few centuries ago, the idea that we could understand the composition of stars seemed absurd. How could we possibly determine what distant suns are made of when we can never visit them or collect samples? Yet spectroscopy gave us that ability. We learned to read the chemical fingerprints encoded in starlight. The story of how this became possible is instructive. In the early 1800s, the philosopher Auguste Comte declared that the chemical composition of stars would forever remain unknown. It seemed like a safe prediction. Stars are so distant that travelling to them was and remains impossible. How could we possibly analyse their chemical makeup? But Comte had not anticipated the development of spectroscopy. When light from a star passes through a prism and splits into a rainbow of colours, dark lines appear at specific wavelengths. These lines are absorption features created by chemical elements in the star's atmosphere. Each element produces a unique pattern of lines, like a fingerprint. By comparing these patterns to those produced by known elements in the laboratory, astronomers could determine what stars are made of. This discovery transformed astronomy. We learned that stars are made primarily of hydrogen and helium, that different stars have different chemical compositions reflecting their ages and histories, and that elements heavier than helium are forged in stellar interiors and scattered into space when stars die. All of this became knowable through spectroscopy, a technique that seemed impossible before it was invented. A century ago, the idea that we could observe the first moments after the Big Bang seemed like fantasy. Yet the cosmic microwave background radiation gave us precisely that capability. We can now see the universe as it appeared when it was less than 400,000 years old, long before Earth or even the Sun existed. The cosmic microwave background was predicted before it was discovered. In 1948, Ralph Alpher and Robert Herman calculated that if the Big Bang really happened, there should be leftover radiation from that event, cooled by the expansion of the universe to just a few degrees above absolute zero. For nearly 2 decades, their prediction was largely ignored. Then in 1964, Arno Penzias and Robert Wilson accidentally discovered this radiation while testing a radio antenna. They were initially puzzled by a persistent noise in their equipment that seemed to come from all directions in the sky. Only after consulting with astronomers did they realize they had detected the cosmic microwave background. This accidental discovery opened a new window onto the early universe. By mapping tiny temperature variations in the cosmic microwave background, astronomers could study conditions when the universe was a cosmic infant. They could test theories about the Big Bang and measure fundamental cosmological parameters with unprecedented precision. What once seemed impossible, observing the universe shortly after its birth, became routine. More recently, the detection of gravitational waves seemed almost impossible. Einstein predicted these ripples in space-time in 1916, but he thought they would be too weak to ever detect. For decades, physicists built increasingly sensitive detectors, but gravitational waves remained elusive. The technical challenges were immense. A passing gravitational wave changes distances by amounts smaller than the width of a proton. Detecting such tiny distortions seemed to push the limits of measurement. Yet in 2015, the LIGO detectors succeeded. They observed gravitational waves from colliding black holes more than 1 billion light-years away. This opened an entirely new way of observing the universe, allowing us to detect cosmic events that produce no light. Neutron-star collisions, black hole mergers, and potentially other exotic phenomena can now be studied through their gravitational radiation. An impossible dream became reality through decades of patient technological development and stubborn refusal to give up. These examples show a pattern. What seems impossible at one time often becomes possible later, sometimes through technologies that could not have been anticipated, sometimes through theoretical breakthroughs that change our understanding of what is possible. The multiverse might follow this same pattern. Methods that seem impossible today might become routine in the future. Or we might find that some questions truly are beyond our reach, but we will not know which unless we try. Perhaps in another century or two, the idea of observing or testing multiverse theories will seem just as natural and achievable. Or perhaps we will discover that some questions lie permanently beyond our reach, that some fog can never be cleared. Either outcome would tell us something profound about the nature of reality and our place within it. For now, we stand at the frontier, gazing out into vast clouds of unknowing. We have our theories and our mathematics. We have our observations and our instruments. We have our curiosity and our determination. We peer into the fog, hoping to catch a glimpse of what lies beyond, knowing that even if we never reach certainty, the act of looking has value in itself. The multiverse, whether real or not, serves as a reminder of how much we still have to learn. It reminds us that the universe is far stranger and more wonderful than we ever imagined. It challenges us to think bigger, to question deeper, to never become complacent in our understanding. Edward Quinn's historical atlas depicted the expansion of geographical knowledge, the slow clearing of clouds from maps of Earth. We are now engaged in a similar project, but our atlas charts something far more vast and mysterious. We are mapping not just one universe, but possibly many. Not just physical space, but perhaps all of mathematical reality itself. The clouds still linger. The fog still obscures. But with each passing year, with each new discovery and theoretical insight, we push a little further into the unknown. We blow away a few more wisps of cosmic fog. We reveal a bit more of the grand structure that lies hidden just beyond our sight. And perhaps, if we are fortunate and persistent, we will one day look back on this era the way we now look back on the debates about the size of the universe in the 1920s. We will marvel at how much we did not know, how limited our vision was, and we will be grateful to those who dared to peer into the fog, who refused to accept that what we can see is all there is. The journey continues. The questions remain. The fog still beckons. You have been exploring the concept of the multiverse, from its simplest forms to its most speculative possibilities. The ideas discussed here represent some of the most profound and challenging concepts in modern physics. Whether any of these multiverse theories turn out to be correct remains to be seen, but the search for answers continues, driven by curiosity and the fundamental human desire to understand our place in the cosmos. Thank you for joining this exploration into the nature of reality itself. May you find peace in the mystery, wonder in the unknown, and joy in the eternal quest for understanding.